All right, so this is a video on section 3.1, which is on numeration systems. We're going to talk all about numbers today. We're going to start by talking about different types of number systems that have evolved throughout our human history before people started using the base 10 system that we use today, the Hindu-Arabic system. And then we're going to talk a little bit about some base 10 pieces, and then we're even going to talk about how to do some computations with different bases, and then we're going to end with some rounding. So this is a long lesson. I'm going to try to do it in one video. We'll see how it goes. I might have to split it up, but I think this is one of the longer lessons of the course because it really just lays the foundation for everything we're going to do in the rest of the course, and it's really a great foundation for just elementary school math in general. So I think hopefully you'll find a lot of this relevant. So we're going to jump in and start talking about the Egyptian numeration system. Now, some of these numeration systems, like the Egyptian, the Babylonian, the Mayan, they're not used today. They won't be on your exam. But I think these are fun to kind of explore a little bit, just to get a taste. I mean, we don't have to spend too long, but just to have an idea of, what different types of number systems look like, and I think these would be fun to do with elementary school students at some point. So let's jump in. So we're going to start with the Egyptian numeration system. It was developed around 3400 BCE. It involves grouping of 10, so it's similar to the base 10 system we use today. So for example, if I had a number 3,452, that represents 3,000. So this is the thousandth place. So 3,000s. This represents 4 hundreds. We've got 5 tens and then 2 ones. So if you look at our place values, you've got the ones place, the tens place, the hundreds place, the thousands place. That's very similar. It's the same numbers that you see here in the Egyptian numeration system. The huge difference, though, we've got a couple of differences, but the main difference here is that with the Egyptian numeration system, there's no place values. So if you want 3,000s, you literally have to write, like it would be us writing 1,000, 1,000, 1,000 every time you want 1,000. So it gets a little bit cumbersome. It's also cumbersome because there's pictures instead of numbers, so it takes quite a bit longer to draw these pictures out. So let's try an example. So this first example, you can just read, look at the chart with the pictures. The lotus flower is 1,000. So if you have 2 of those, it looks like we've got 2,000. We've got 3 hooks, so 300. Looks like we've got 4 heel bones, which are worth 10 each, so that would be 40, and then 2 sticks, which are 1 each, so that would be 2. So we could write it out, 2,000 plus 300 plus 40 plus 2. We're calling this an additive system, so it explains in the box below, but we're basically just adding up all of the different values of each of those symbols. And so that gives us the number 2,342. Now, if you want, you could pause the video and try the next one if you like. For the next one, you should get, so we have 10,000. These together, that would be 1,000 each, so 4,000, 20, and then 6. So if we add all of those up, we get 14,026. And you can imagine, think for a minute, if the Egyptians had to write a number as big as like a million or a trillion, it would take a long time. That's a lot of pictures. So that's one downside of this system, having an additive system. It's definitely more time consuming. But this would be fun for kids. Kids would definitely enjoy exploring this system, I think. So the Roman numeration system, this one you will see on your test, and the reason you're going to see it in your homework and on your exam is because we still use this in our world today, and students in elementary school learn Roman numerals as part of their math curriculum in most schools. So I think it's definitely something that we want to get a handle on. So Roman numeral system is a subtractive system. And a subtractive system basically is any type of system where, you're using subtraction to get certain, values for symbols. So one mnemonic that you can use, I wrote it down here to remember some of the Roman numeral symbols, is my dear cat loves extra vitamins intensely. So that represents all of the symbols, at least up to 1,000 in the Roman numeral system. So, and these are not symbols that you have to memorize by all means. I mean, you're going to have your notes, especially, you know, when you're doing your homework and for your exam. So you can write those down, and it's not anything you have to memorize. But let's just jump down and do example 2, and then we can kind of talk about what it means to be subtractive system. So basically what you're going to do for Roman numeral system is it's an additive system until you reach the number that comes right before the next symbol. So if the first symbol is 1, okay, and then the next symbol is V, which stands for 5, the number 4 is the number that we're going to use the subtractive symbol for. The next symbol, 10, which is an X, the symbol before that, 9, we're also going to use the subtractive system for that. So let's start with number 2. So 2 would just be 2 like this. 3 would be 3 like this. 4, it's tempting just to say 1, 2, 3, 4, okay, but that's not right. You have to use the subtractive system. So what you do is you say, okay, how can I get 5 by using subtraction? Or I'm sorry, how do you get 4 by taking the number 5 and using subtraction? Well, you take 5 and you subtract 1. And the way that you write that is you write a 1 first, the symbol for 1, and then the symbol for 5. So IV, okay, this is 1 and this is 5, okay, tells you to take 5 and subtract 1, and then you get 4. Okay, so IV is 4. And then from there, we use the additive principle, where we start, if V is 5, then to get 6, we just add a 1. So 5 plus 1 is 6. 7 is 5, 6, 7. And you can put a line on top and bottom, or you could just leave it out to make it quicker. 8 is 5, 6, 7, 8. Okay, for 9, it's tempting to say 5, 6, 7, 8, 9. Okay, that would make life easy, but that doesn't work. 9 is the number right before the next symbol X, so we have to use the subtractive system. So we're going to take X, which is 10, and we're going to subtract 1 to get 9. So you're going to put the 1 in front. So whenever you want to use the subtractive system, you're always going to put the smaller number first. So this number is smaller on the left, and then the bigger number is on the right, which I know seems so odd because really it's opposite of what you're doing. You're doing 10 minus 1, which seems like you would put the X first, but this is how it works. So it's going to be 1X. So 1X is 9. Okay. And to make this simpler, I'm just going to jump ahead here. I made this chart, and I think this is a helpful chart if you keep, so I'm just going to star the ones that I would keep handy. I would keep this chart right here handy. And you know what, I'm going to use a different color. So I keep that chart handy, and then I would also keep this chart handy. And I think with both of these charts, you'll be good to go. And so what I have here is just a list of all the compound numbers, they're called. So 4 we said was IV. We said 9 was IX. So we're just going to make a list of those numbers that involve subtraction, and that way you can look out for those. And so let's go up and fill out the rest of the table, or you could pause the video and try it on your own. So if X is 10, 20 would be 2 of those. So 10, 20, 10, 20, 30. Okay, notice L is a new symbol, C is a new symbol. So I'm just going to circle the numbers that come right before, because we're going to have to use the subtractive property for those. So to get 40, we're going to do 50 minus 10. Well, 50 is L, 10 is X, and I write the smaller one, X, before the bigger one, so it's XL. So I'm also going to write that down here in my subtractive property compound number chart. Okay, and so if L is 50, 60 would be 50 plus a 10, so 50, 60, 50, 60, 70, 50, 60, 70, 80, okay? 90 is directly before the 100, so to get 90, I'm going to take 100 and I'm going to subtract the 10. 100 is C, 10 is X, so I'm going to write the X before the C. So 90 is XC, okay? Same thing down here. So 100, I've got a new symbol, is C. So 200, 2 C's, 300, 100, 200, 300. 400 is directly below the next symbol, D. So I'm going to take 500 and subtract 100 to get 400. So 500 is D, symbol D. 100 is C. So I'm going to say C, D. And then for 600, I'm going to use just the additive property. So I'm going to take 500, which is D, and add another 100. So 500 plus 100 is 600. And then 500, 600, 700. 500, 600, 700, 800. And then 900, okay, is directly before the next symbol M, which is 1,000. So I'm going to take 1,000 minus 100 to get 900. So 1,000 is letter M, 100 is C. So I'm going to write that C, M, and I'm going to fill that down here. And 400 is C, D. Okay. I usually just don't even bother putting the lines on top and bottom just to make it simple when I'm doing it on paper. Let's jump in and let's do example 3. So I'm going to let's start with the first one. So one way that you could do this is you could just look at this compound number chart and keep an eye out for 4, 9, 40, 90, 400, and 900. Like keep an eye out for those combinations. So like as I look at this number, I see this XL right there. I can circle it. That's going to be 40. I see IV. That's going to be 4. Okay. And the M and the C, those aren't in my compound number chart. So I don't see MC or CC. So I'm just going to directly write down what those are worth. Okay. So, and if you forget what they're worth, remember that you've got that chart on the following page that I circled in red. So M is 1,000. So you can write down what each of those are worth. So we've got M is 1,000, and then C is 100. So 100, 200, 300. So that would be 300 total for those 3 C's. So it looks like we have 1,344. And if you're not sure, you could always just add up those numbers. You can use your calculator if you need to, or add them up on the side, just like that to get the result. Okay, same with the next one. So keep an eye out. I'm noticing that CM, okay, CM is 900 from my compound number chart. It looks like XC, is 90, okay. M and M, those are both worth 1,000. So this would be 2,000 and then 3. So we've got 2,993 for that one. And then last but not least, looks like I've got XL there, which is 40, and then I've got IX, which is 9, and C's are worth 100 each. So I'm going to write down 200 for those 2 C's. So I've got 249 for that one. Okay. So now I'm going to go backwards. For example 4, now I've got the number, and I'm going to write it using Roman numerals. So 979. So if I break that up, I'm just going to break it up. This is called expanded form. We'll talk about this a little bit later. 900 plus 70 plus 9. So ask yourself, well, how do you write 900? That's in our compound chart above. So 900 is CM. So I'm going to write CM for 900. 70 is not in our compound number chart. You can scroll up if you want to identify how to write 70. We did that above. So that would be LXX for 70. So CM LXX for 70, and then 9 is in our compound number chart. That's going to be IX. Okay. So our answer is CM LXX IX. And then finally for 3,054, I'm just going to write that in expanded form. So I have 3,000 plus 50 plus 4. So the 3 is in the thousands place, the 5 is in the tens place, representing 50, and then we have 4. I don't need to write the 0 because that's just a placeholder. So for 3,000, I'm going to write 3 M's. M is worth 1,000 each. So 3,000, and then 50 is an L, and then 4 is IV. So MMMLIV. And you may be asking, when am I going to need to know this? Again, it rarely comes up in real life, but there are situations where we do see Roman numerals in real life. I'm sure you can, you know, remember Super Bowls and things like that. But it's not super common. But it's still common enough that it's worth talking about and worth being able to understand, so we can also teach kids too. Okay, so the Babylonian numeration system, let's jump into that one. So this is one I'm just going to kind of briefly talk about and not get in too deep. You're not going to have to do this on a test or anything. I just think this one is interesting. So the Babylonian system is base 60. So keep in mind, so in our system, we have base 10. We use digits 0 through 9. Okay, which is actually 10 digits when you count those out. So for base 60, they use digits 1 through 59. They actually didn't have a symbol for 0 in the Babylonian system. So that was definitely a downside to using this system. But this one actually used place value. So we haven't talked about one that uses place value yet. And so the place values it combined place values and symbols. So we've got this symbol for 1 and then this symbol right here for 10. So for example, like if we wanted to look at this picture right here, if we separate, we've got 1, 2, 3, 4, 5. So there's your 50, and then 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's your 59. I'll just scroll down real quick here and show you real quick how they use place values. So take this example right here on the right, and these would be the place values. So you have this place here, and then here, and then here. So each place value, okay, represents a group of some multiple of 60. So this first place value on the right is 60 to the 0 power, which is just 1, 60 to the first power, which is 60, 60 to the second power, which is 3600. So those are the sizes of the groups, okay? And then these symbols tell you how much of each group you have. So these symbols right here are 10. So 10, 20, 30. It means we have 30 groups of size 1, so that's where you see the 30 times 1. Right here we have 1, 2, 3 groups of size 60, and right here we have 10, 20, 1, 22, so 22 groups of size 60 squared, or 3600. And then if you add all that up, you get 79,410. If you're thinking, gosh, this sounds so confusing, it is a little bit. It's definitely more confusing than the system that we use now, but just, you know, interesting to kind of see how different parts of the world use different number systems. Okay, so the last one we're going to talk about that we don't use today is the Mayan numeration system. So this one I thought was interesting, and I wanted to bring this up because it's a base 20 system, and they use place value, but they actually wrote their numbers vertically instead of horizontal. So if you look down here where it says examples, you know, here's the place values. They're stacked on top of each other like this. So we've got, in this number, there's actually 4 place values. And you know what, I'm going to cross off. This is actually a typo from the book. I copied and pasted this from the book, but this isn't right. This should be 65,526 there. But basically what's really interesting is the Mayan year was broke up into 18 months with 20 days each. And that relates to their the place values that they actually use. So if you check out these numbers right here, so where you see the 18 times 20 and 18 times 20 squared, that has to do with the 18 months of the year and 20 days each. So their first place value is the ones place. The second place value is the 20 place. Their third is 18 times 20, which is the 360 place. And then the next one would be 18 times 20 squared, or 7,200 place. So, and then the symbols tell you how much of that group that you use. And when you add all of that up, you end up getting 65,526. So again, this isn't something that you need to like be concerned about actually doing yourself and working out. I just thought I'd show you how another system works. And if you want, you can check out this box. It tells you a little bit more about how the Mayans incorporated the 18 months and the 20 days each into their mathematic system, and this pyramid at Chichen Itza. So all that said, let's jump into the system that we use today. So the system we use today is called the Hindu-Arabic system. The system originated in India in the 6th or 7th century. It was introduced to Europe by Middle Eastern mathematicians. And it really paved the way for algebra. So once this was introduced, those other systems started to sort of, get smaller, and they were used less frequently, and then eventually this took over. So the digits that we use today, I'm not talking about numbers, I'm talking about, think symbols when you see the word digits. So what symbols do we use in our number system? We have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have a base 10 system, and we have 10, oops, you know what, not 10. I'm actually glad I made that mistake. Let's talk about that for a minute. Is 10 a digit? 10 is a number in our system, but it's not a digit because it consists of 2 digits. So we already listed 1 as a digit, and we already listed 0. So I don't need to list 10 as a digit. That's a number. So every number in our system, for example, 356, it's a number, but it in and of itself is not a digit. The 3 is a digit, the 5 is a digit, the 6 is a digit. So we have 10 digits altogether, 0 through 9, and using these digits we can create any type of number in our system. So we call it a base 10 system. Why? And that's what this question down here is asking. So the reason we call it base 10 is because we count things. We count in groups of 10. Or multiples of 10 often. Okay, so for example, let's say we have the number 537. Okay, we've got 3 place values there. We've got the hundreds place, the tens place, and then we have the ones place. So this tells us we need 5 groups of 100, we need 3 groups of 10, we need 7 groups of 1, and if you add that up, you end up getting 537. Okay. Now the nice thing about groups of 10 and having a number system in base 10 is that every time you go to an additional place value. So for example, I'll just kind of write this out. So we start with the ones place, and then the tens, and then 100, and then 1,000, and then 10,000. What's happening? I'm just adding a 0 each time. So it makes it so much simpler in terms of finding our place values. Makes it simpler in terms of writing the number too. So let's real quick, where it says naming Hindu-Arabic numerals, let's talk about how to name this number. So we've got down here, and this would be a great place, pause the video and see if you could say this number in your head or out loud. So we've got the hundreds, we have the thousands, we have the millions, we have the billions, we have the trillions, and then, do you know what that's called? Might have heard of it before or not, quadrillion. Okay. My kids are always asking me, what's the biggest number? What's the biggest number? And I'm like, well, there's technically no biggest number because they keep on going, but a Googleplex is a really big number. You should check that out. Google it if you haven't heard of it. But quadrillion is also pretty big too. So let's do some examples with some base 10 numbers. So let's say I have $2,892 saved. What does that mean? So see if you can pause the video, and I want you to tell me how many groups do I have, and then what size are each of these groups. So this column here, this is going to be the size of the group. So what are my place values? I have 2 groups of, that would be the thousands place. I have 8 groups of 100. I have 9 groups of 10. And I have 2 groups of 1. Okay. We can write numbers in what's called expanded form, and we've already done that a couple times, but let's talk about that. So we're basically breaking up the number in each of the place values. So this is something that elementary school students do quite a bit, starting as early as 10th, or not 10th grade, first grade. They do this in 10th grade, but you know, much more advanced. So I would say in first grade, first and second grade, they start working on this quite a bit. And then as they get older, the place values get bigger. But let's talk about how to write expanded form of 83,507. So you look at each place value, and then you're going to write the group times how many you have, or how many you have times the size of the group. So I'm going to start with 8, and I'm going to say I have 8, that's the 10,000s place, plus I have 3,000 plus 500 plus I have 0 tens, that's optional. If you want to leave that out, you can, plus 7 ones. Now, I'm going to write it in this chart above, 83,507. Let's check out those groups, and let's see if we can write them with an exponent, because that's another way you can write expanded form. So 10 is 10 to the what power? 10 to the first. 100 is 10 times 10, or 10 squared. 1,000 is 10 to the third power. 10,000 is 10 to the fourth power. And you might be asking, well, what about this one? Did I forget about it? I didn't forget about it, but it's good to come back, because now we can see a pattern. So we have 10 to the fourth, 10 to the third, 10 to the second power, 10 to the first power. What happens if we decrease that exponent one more time? 1 minus 1 is 0. Well, what happens when we have something to a 0 power? Try it with your calculator. Do 10, that little caret key, to the 0 power. You'll end up getting 1. So any number to the 0 power is 1. And so we can use this pattern to establish all of the place values. Again, our system being base 10 makes it a little bit easier. We don't really have to even write the exponents, because we can just add a 0, but this is helpful to know, especially when we get to different bases a little bit later. So an alternate way to write expanded form would be 8 times 10 to the fourth plus 3 times 10 cubed plus 5 times 10 squared plus 0 times 10 to the first plus 7 times 10 to the 0 power. So I would say either or totally work. The bottom one is going to be where younger students start for sure. They're not going to write exponents until they get to probably like 5th grade. So let's look at example 5. Express the following numbers in expanded form. So this would be a good time. Pause the video and try these on your own. With this second one, these middle two terms, I would say this is optional. It's not wrong if you leave them out. It's not wrong if you leave them in. I think when students start, especially kids start doing this, it's helpful to leave them in, just so that you are acknowledging that there's those place values there and you don't lose your spot, kind of like putting placeholder zeros when you add and subtract. But you know, even like that, it's optional. Example 6, what number does the expanded form represent? So you could work this out by hand. You could also use a calculator. So you're actually multiplying 3 times 27 plus 2 times 9 plus 1 times 3. So we've got 81 plus 18 plus 3, we get 102. Now, did you notice in this one, you might be thinking, okay, well, our groups, so we have a group of 27, a group of 9, and a group of 3. So that's not base 10, because those numbers are not 10. So we can actually do computations and write numbers in different bases, and this is kind of alluding to that. And if you think about our base 10 system, in our base 10 system, we started with 10 at the very right. Well, we started with 1, but 10 was the next place value. This would be a base 3 system, because you've got a 3, and then 3 times 3 is 9, and 3 times 3 is 3 times 3 times 3, 3 cubed is 27. But but we'll come back to that later. I wouldn't worry about that right now. The next one, if you work that out, so 6 times 10 to the 5th, that would be 6 times 10. We've got 5 zeros there. 1, 2, 3, 4, 5. Plus 3, a 1, and 3 zeros. Plus 9 times 1. So you should get 603,009 for that one. All right, so my favorite part, models. When kids learn about numbers, okay, starting in pre-K, we use models. So we have them use blocks, we have them use some sticks, anything, stickers, toothpicks, markers, marbles, anything that you can use to help them count physical objects. And it should be, I know I highlighted it here, this should be a major part of mathematics instruction in elementary school. This is a recommendation from Common Core and the NCTM, which is the National Council of Teachers for Mathematics. And if you are a type of person where you don't prefer to use models, you'd rather just do the computations by hand, I'd encourage you to have an open mind. I will tell you there's lots and lots of kids that when they are introduced to playing with physical objects, all of a sudden the light bulb goes on and things start to make sense. I have a child, for example, who she's going into 3rd grade, who repeatedly uses base 10 pieces when she adds or subtracts. Even though she knows how to do it by hand using the standard algorithm, she absolutely has to draw it out every single time, and it takes her longer, but for some reason, it just makes sense to her. So so let's talk about how you could use these to actually add and subtract. So bundle of sticks model, for example, you might have kids, you might tell kids, okay, you have 1 stick and that's equal to 1, and they could group them in groups of 10. 10 groups of 10 would be 100. Basically, you're modeling base 10 pieces. So what a base 10 piece is, and I would say most elementary schools should hopefully have sets of these, like actual blocks that look like these blue pieces. If they don't, you can actually print these off and you can laminate them and you can work with them that way. You can also just draw them on a piece of paper, but we call the unit is worth 1, a long is worth 10, a flat is 10 by 10, which is 100. And then I'm going to draw the next one. It's not going to be to scale, but imagine if you put 10 flats together, so that'd be 10 times 10 times 10. We call this a cube. So this is 10 to the cube, 10 times 10 times 10, and that would be worth 1,000. So these are visual models for our place values in base 10. Okay, so we're going to use those to express the numbers in example 7. I will say that when I'm drawing these on paper, I usually just do a quick square for a flat, I do a stick for a long, and then a dot for a unit. I encourage my kids to do this too, just because it takes a lot longer when you draw the square for the unit and the rectangle for the long. So you may want to try that. So for example 7, so we're going to start by drawing the number 39 with our blocks. So 39, that would mean I'd have 3 longs, so 10, 20, 30, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's how I draw 39. 115, so that would be 100, so a flat, 10, 1, 2, 3, 4, 5. So you can break it down. Every digit is associated with a different size piece. Okay, 327 means 3 flats. So 300, it means 2 longs, and it means 7 units. And then 536 would be 5 flats. So 500, 30, 3 longs, and 1, 2, 3, 4, 5, 6. So we introduce this by just having kids practice lots and lots of times. You give them a number, they make it with the blocks. You give them a number, you make it with the blocks until they become really familiar of drawing the picture. And you could do that with yourself also. I mean, you could make up numbers and draw them on the page just to practice drawing those pictures. Then once you have the pictures, the next part Example 8 is when we use, it's called regrouping. And you're going to see these words, like if you ever look up like a Common Core worksheet online for kids, you'll see the word regrouping quite a bit. And what regrouping means is anytime that you have a group of 10 or, well, yeah, 10 or more, that means you can use the next size piece or go to the next place value. So for example, we know that a long is 10 units. So in this example A, I could count 1, 2, 3, you know what, I'm going to use a different color. Might help. So I'm going to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 units, if I put them together, make a long. So I'm just going to draw a long and cross this off. It's basically like an exchange. So regrouping is like an exchange. Now I'm going to go through and I'm going to count the longs. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 of these makes a flat. So I cross those off. I made the exchange. It looks messy. Now I need to actually write down what my answer is. So determine the base 10 number represented by the collection. So if I have, I'm just going to write over here, flats, longs, units. Those are my place values. So I have 3 hundreds left. I have 2 longs left, and I have 2 units left. So my base 10 number is 322. Okay. Try B and C on your own. So if you want, pause the video and try those, and then I'll walk through them. So I'm going to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it looks like I have a group of 10 here. I'm going to exchange that for a long. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I've got another group of 10. Exchange that for another long. Okay. And so over here, when I am writing my final number, if you want, you can do it now. So it looks like I have 4 units left over when I make my exchange and do my regrouping. So now I'm going to count up all my longs. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that makes a flat. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And it looks like that makes a flat. And it looks like I have 1 long left over. And I have 2 flats. So my number, my base 10 number, is 214. So unless I regroup, looking at this picture initially, I could still determine that I had 214, but it would just take me a lot longer. So with C, let's go ahead and do regrouping. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That equals a long. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We've got another long. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we've got, so it looks like we've got 3 longs out of that. So I'm just going to write down, we've got flats, longs, units. So left over, I have 2 units after I regroup. And then longs, I'm going to count those. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is just lots of counting of 10s. That makes a flat. And then 1, 2, 3, 4, 5, 6, 7, 8, 9. So I don't quite have another group. So I have 9 longs left over. I'm just going to leave those there. And then I've got 2 flats. So my number is 292. Okay, those are problems I would definitely go back and try to redo on your own if you didn't do them by yourself right then, because they're really crucial in understanding what comes next. So let's talk about some other bases. So we talked about base 10. So in base 10, we have digits 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So we have 10 digits, okay? And then we have place values that go 10 to the 0, 10 to the 1, 10 to 2, 10 to the third power, 10 to the fourth, keeping going in the left direction. So if we have base 5, okay, we're counting in groups of 5, okay, instead of 10. The digits that we would use would be 0, 1, 2, 3, 4. So you stop right before 5, just like in base 10, you stop at 9, and that's right before 10. So what are the place values? You'll have 5 to the 0 power, 5 to the first, 5 squared, 5 cubed, 5 to the fourth. So 5 to 0 is just 1, 5 to the first is 5, 5 squared is 25, 5 cubed is 125, and 5 to the fourth is 625. Now it keeps going. I just decided to stop there, but you can keep on going forever with those place values. So what do the base 5 pieces look like? So we still have a unit, so we call this a unit. If we're doing groups of 5, it means that we put 5 of those together, okay, to make, we still call this a long, but it's worth 5, okay. We have a flat, so we call this a flat, but instead of 10 by 10, now it's just going to be 5 by 5. Pretend like this is drawn correctly or to scale. So this would be 25. And then I'm going to do one more. This one is kind of weird. It's called a long flat. And it looks like a long flat because it's longer, but it's not like our cube. When you have 10 times 10 times 10, it makes a perfect cube. Well, when you have 3 flats that are put together, so 5 times 5 times 5 is 125. Or I'm sorry, it wouldn't be 3. It would be, yeah, it'd be 5 to the third power, but that would be 5 25s put together. So it would look like this. You'd have one of those squares, 2, 3, 4, 5. So notice the place values go 1, 5, 25, 125. So to get 125, you're taking that flat and you're putting 5 of them together. So we've got one big long piece, which is called, I'm just going to change colors real quick so you can see the long flat is just one big rectangle that's worth 125. So let's do an example in a different base. And if you're thinking, why are we talking about a different base? Why wouldn't we just focus on base 10 when that's what we use? Well, the reason is I feel like using different bases allows us to have a deeper understanding of how we use base 10. And I think one of the biggest, most important things that you can understand as a math teacher in elementary school is how the base 10 system works, and why, we use our strategies for adding, subtracting, multiplying, and dividing. And so I think this gives you a deeper foundation and understanding to the base 10 number system. So just hang in there with me if you're thinking this is a little weird, because it is, but it's really similar to what we do with base 10. So if I had you say this 2, 3, 1 base 5 cookies, then that would be 2 groups of 125, because this is the 125 place value. Or I'm sorry, no, that wouldn't be the 125. I didn't count right. Let's go up here. So if I had a number, I'm going to actually, you know what, let me scroll up and I'm going to write it right on top of these place values so it makes more sense. So I'm going to start with the 1. Oh, but now my pen isn't working. There we go. So 1, a 3, and a 2. So 231. So we've got 2 groups of 25. We've got 3 groups of 5. And then 1 group of 1. Okay? So we could write it like this. 2 groups of 25 plus 3 groups of 5 plus 1 group of 1. And if you multiplied and added those together, you get 66. So this is the expanded form. Okay? And this is the base 10 number. So the number 231 base 5 is the same thing as 66 in base 10. And notice 66 is a shorter number. When you have higher bases, you don't need to have as many place values to make as big of a number. When your bases are smaller, you have to have more place values because you're adding more up. So how many symbols does base n have? So let's think about this. So we said base 10 had 10 symbols. 0 through 9. We said base 5 had 5 symbols. And that was 0 through 4. Okay, so base n, whatever the base, is going to have n symbols. Whatever number the base is, that's how many symbols it's going to have. So let's practice in base 5. So it says express 1, 2, 3 base 5 in base 10. So these are the easier problems to do. I'm not saying they're easy, but they're easier because they're telling you how many of each group you have, and then you're just writing in an expanded form. So in this first row, we're going to put place value. And then the second row, we're going to place the number of groups. So for base 5, the place values are 1, 5, 25, 125, 625. You don't have to memorize these. Remember, you can always get these by using exponents. So if you forget, use the exponents, and then it does keep going. I'm stopping there because my number 1, 2, 3, you always write the number. I'm going to use a different color. So we've got this number 1, 2, 3 base 5. That's going to come down there, okay? And you always put it as far right as you can. So now what we do is we are going to write it in expanded form. So 1, 2, 3 base 5 means that you have one group. Oh, that's way too thick. You have one group, that's better, of size 25. You have two groups of 5, and you have three groups of 1. So I'm taking this number in red and I'm multiplying it by that one. Okay, so I'm multiplying these and then I'm adding them together, just like in base 10. And so if you work that all out, you end up getting 38. So 1, 2, 3 base 5 is the same thing as 38. It's just a different way to write it. Okay, so let's try another one. So our place values, I'm going to put on top. Same as the last problem. And then our number, 3, 4, 1, 2. And it's really important you put it all the way to the right. So the far right number represents the one place. You do not want to write it like this. Then you would get the question wrong. So you always want to slide it as far right possible. So that last number, that digit 2, represents the ones place. Okay, so now we're going to write it in expanded form. So it means I have 3 groups of 125 plus 4 groups of 25 plus 1 group of 5 plus 2 groups of 1. And if you work all of that out, you end up getting 482 for that one. Okay. So these questions, these are a little bit harder. So I'm going to call these are harder questions because you have to find the number of groups. Okay, so these this next one, convert 97, that's a base 10 number, to base 5. So I'm going to write out my place values like before. So I'm going to start with 1, 5, 25, 125, 625, and you might have to keep going. The trick here though is if you have 97, you only have to go until you reach the number. Any number that's higher than that, you're not going to need that size group. So if you have 97 marbles, you can't make a group of 625. You can't make a group of 125. So we're not even going to need those. So you can cross those off if you want, or just don't even bother making those. So I'm going to take my number 97, and what I'm going to try to do is figure out, well, how many groups of each size? Try to make the biggest group possible. So I can't make a group of 125 because I don't have enough, but I can make a group of 25, and I can actually do it a couple times. So I can subtract 25, and then I have more, and then I can actually subtract 75 or 25 3 times. So I can make 3 groups of 25 there. So 97 minus 75 is 22. Okay. Then you ask yourself, well, how many groups of 5 could I make of that? So you go to the next place value. Well, you could take off 5, and if you wanted, you could write this, you know, you could do this. You could subtract 1 at a time. It's just a little bit faster the other way, but this sometimes makes more sense. So you could subtract 5 and get 17. Oh, then I have another 5, so you could take off 5 again. And then I have another 5, and you could take off, and then you can make another 5 out of that and subtract 5 again, and you end up getting 2. So how many 5s? I subtracted 1, 2, 3, 4 5s. So I'm going to take 4 groups of 5. And then I have 2 left over. So that means I want 2 groups of 1. So I'm going to subtract 1 twice. and then I'm left with 0. So the goal is to get to 0 and keep subtracting the groups until you get 0, and then write down how many groups you have. And then when you're done, double check to make sure that it works. So 3 groups of 25 plus 4 groups of 5 plus 0 groups of 1. And if you work that all out, you end up getting 97, which is what we started with. So the answer, sometimes it's hard to actually know, like, well, what is the answer? The answer is 3, 4, 2. Oh, and you know what? I put a 0 here. This should be 2 because I subtracted 1 twice. So there are 2 1s here. The answer is 342 based 5. So that number is the same thing as 97. So 3 25s, 4 5s, and 2 1s are the same thing as 9 10s and 7 1s, or 97. So let's do the next one. So 341 in base 5. So I'm going to write my place values. Now, at this point, I say, okay, well, if I have 341, write that down or put that in your calculator. I don't need 625, it's too big, so I'm going to cross that off. But I can do, I can make a group of 125. I can do it a couple times. So I could take off 125. I could do it again. So I did it twice here. So once, twice. I can't do it again because I don't have enough. I'm left with 91. So I made 2 groups of 125. And then I'm going to subtract 25 and 25 and 25. So that's 75. So I have 3 groups here of 25. And if I subtract 75, I end up getting 16. And then I could subtract 5 and again and again. Okay, until I have 1. So I had 3 groups of 5 that I was able to make. And then I have 1 group of 1 to get to 0. So my expanded form is 2 times 125 plus 3 times 25 plus 3 times 5 plus 1 times 1. And if we work that all out, we end up getting 341. And my answer is 2331 base 5, which is just the number that's in the box, okay? The number of each of those groups. All right, so let's go down to example 10. So more bases. So notice these questions have different types of bases, but it works the same. So with base 2, you're going to start with 2 to the 0, 2 to the first, 2 squared, 2 cubed, 2 to the fourth. 2 to the 0 is just 1, 2, 4, and you can use a calculator if you need to write out all the place values. And then if you're told the number, okay, this is an easier of the two problems because you're just going to put this number down here. So 1, 1, 1, 0, 1, and then you're going to write it in expanded form. So 1 group of 64 plus 0 groups of 8, I'm just multiplying these numbers here, plus 1 group of 4, plus 1 group of 2, plus 1 group of 1. And if you multiply that all out, I get 23. Okay. Same thing with the next one. So I'd try this one on your own. So you're going to put this number in the box on the second in the second row. So 4, 3, 2, 1. Now this one is a different base. It's base 8. So you're going to use your exponents. 8 to the 0, 8 to the first, 8 squared, 8 cubed to find my place values. So it's 5, 12, 64, 8, and 1. And then you're going to use expanded form to multiply. So you have 4 groups of 512 each, 3 groups that are size 64, 2 groups that are size 8, and 1 group of size 1. And then if you multiply that all out, you should get 2,257. Okay. So the next two, these are harder. Okay. I'm going to erase this just so that I have a little bit more room to work here. So this next one, we've got base 6. So let's write out the place values. So 6 to the 0, 6 first, 6 squared, 6 cubed, 6 to the fourth. Okay. And you can use a calculator to write out what those numbers work out to be if you need to. And then we're going to take the number 6,135. So this is, let me rewrite that, it's messy. I would use a calculator for this. I would put 6,135 in your calculator, and I would keep subtracting until you can't subtract anymore. So if you subtract 1,296. Oh, and you know what? Let me say something real quick. How do you know you need to stop at 1,296? Well, I would actually go and do 6 to the 5th power just in case. If you do 6 to the 5th power, it's a number that's bigger than 6,135. So that's why I ended up stopping at 6 to the 4th. But I would keep going as big as you can until you go bigger than the number. So take your calculator, put 6,135. And we're going to start with the biggest group, 1,296, and you're going to keep subtracting, okay? And you're going to keep, so if you subtract, and then you do it again, and then you do it again, and then you do it again. You keep going until you get 951, because at that point you can't subtract 1,296 from that. So how many times did I do it? I did it once, twice, 3 times, 4 times. So I was able to make 4 groups of that size. Now the same thing with 216. So you can actually subtract 216 4 times. So 216 times 4, you're going to subtract that from 951. So minus 216, minus 216, minus 216, minus 216. You can actually do that 4 times and you end up with 87. And then you're going to subtract 36 twice. So minus 36, minus 36. Oh, did I move my, there we go. Okay. So we subtracted that twice, and we end up getting, so I'm going to put a 2 in the box here, and when we subtract that, we end up getting 15. And then ask yourself, well, how many times could you subtract 6? Well, I could subtract 6, and then I could subtract 6 again, which is 12, and I'm left with 3. So I subtracted 6 twice. And then if you're left with 3, that means you can subtract 3 ones to get 0. So 3 is going to go there. So 4, 4, 2, 2, 3, base 6 is the same thing as 6,135. Okay, that's not an easy problem. Take your calculator and you want to double check the expanded form. 4 times that number plus 4 times that plus 2 times 36 plus 2 times 6 plus 3 times 1, and make sure you end up getting the 6,135. Okay, so our video is going a little bit longer than I wanted, but we're almost done, so I'm just going to keep going, so hang in there. Good news is you can pause and come back if you need to. But last one with the different bases, the conversion. So we're going to work in base 3, so I'm going to start with my place values. So 3 to the 0, 3 to the first, 3 squared, 3 cubed, 3 fourth, and I'm going to keep going until I reach a number that's too big, so I know I can't go anymore. So I get 243. If you end up doing 3 to the 6, it ends up being a bigger number than 376, so that's why I stopped there. So now I'm going to put 376 on the side, and I'm going to figure out how many of each size group do I need. So if I take off 243, which is my biggest size group that I have in my table, I get 133. I can't do it again, so I only can do one of those groups. Now 81, I can subtract that once, and I get 52. 27, I can subtract that once, and I get 25. 9, you can subtract that twice there, which is 18, and you get 7. So I took 2 groups of 9, okay, and I'm left with 7. And now my next size group is 3, so I'm going to subtract 3, and then I can actually subtract 3 again. So 7 minus 3 minus 3, or 7 minus 6, is 1. So I subtracted 3 twice, so I'm going to put a 2 here, 2 groups of 3, and then I have 1 left over, so I'm going to have 1 group of 1, and I have nothing left over, which is what I want. I want to end up with 0. So my answer is 1, 1, 1, 2, 2, 1, base 3, and that's the same thing as 376. Okay, so I know that probably seemed fast. If any of that was confusing or, you know, this is all new. So keep in mind that for the vast majority, if not all of you, this is going to be a new concept. So we'll definitely do some more practice problems together. And definitely reach out if you have questions. So let's look at example 11 and then we'll finish with some rounding. So we're still in different bases with example 11. We're just going to write these in expanded form. So for base 8, we can actually scroll up because we already did the work for base 8. Let's see, right here. Let me see, I'll use a different color. So this problem, example 10b, okay, there we are in base 8, okay, that one. We can use those place values. So it looks like for, there we go. Let me change my pen back here. All right, so 657 in base 8 looks like we've got, I'm just going to write it like this, 6 plus 5 plus 7. And then you want to insert the place values. So start at the right hand side. That's 8 to the 0 power or 1. 8 squared, which is 64, 8 cubed, which is 512. So that would be the expanded form. You could, if you wanted to, write it like this. That's another option. Both are considered expanded form. Okay. The next one, we're in base 9. So you could say 8. I'm going to just write parentheses. I always like to start at the very right because that way I can put 9 to the 0, 9 to the first, 9 squared, and 9 cubed. It allows me to count. If you want to actually write it out and calculate what those exponents are, you can, but you don't have to. Okay, so these are either or work here. Okay, so again, why are we doing this in a different base? This gives us greater understanding, hopefully, for our base 10 number system. All right, so last but not least is rounding numbers. There's all kind of resources online and good videos out there for how to round. We're just going to do a couple of examples together, and then definitely through practice and reaching out if you have questions. Hopefully this will make some sense. So, and a lot of you are going to have a lot of experience with rounding and may not even need to go through this. So I'm just going to write down this number bigger. Okay, so the first question asks us to round to the 10,000s place. So we are going to find the 10,000s place. So ones, tens, hundreds, thousands, 10,000. So I have to count like that. I'm sure other people can just look at the numbers, but I always have to start at the right. So we find the 10,000s place. Okay, that's the place value we're trying to round to. And then we look to the number to the right. And if that number is 5 or greater, then we change the number and we increase it by 1. So since the number to the right is a 7, it's 5 or greater, we're going to change that 5 to a 6. So I'm going to write down the whole number, 13126, and then everything else becomes a 0. So the answer to this first one is 131,260, and then that's it. Okay. So for the next one, thousands place, we're going to locate the thousands place. So ones, tens, hundreds, thousands. So thousands place, we look to the number to the right. 3 is less than 5, so that means leave the 7 alone. So our answer is going to be 131,257, and then the rest is 0. So you always round, you always change everything to the right of what you're rounding to a 0, regardless of whether or not you end up increasing the number by 1 or not. Okay, and then last but not least, so we're going to round to the hundreds place. So ones, tens, hundreds. So the hundreds place is where that 3 is located. And then we look to the number to the right. It's less than 5, so it means that we're going to leave that 3 alone, and then these become zeros. So 131,257,300. Okay. There are a lot of other different rounding techniques that we're going to talk about in the following sections, but these are the rules for your standard, rounding techniques that we use. In the world and elementary school and high school and all math classes. So I hope that helps. Thanks for bearing with me here. That was a long video, but definitely reach out if you have any questions.